Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called Bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention. Purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus coni, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention Bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing, but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled, with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites Pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior US states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on US roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The US continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Every year, over 50 million tons of electronic waste are generated worldwide, a weight greater than all the airplanes ever built by man. Some of this equipment disappears into the shadow market, while another part goes to legal centers where gold, copper, and palladium are extracted from it. But what happens to your old laptop after you turn it in at a collection point? Where do the hard drives with personal data disappear? And how is pure gold of 99.9% purity born from a pile of scrap? Watch until the end, and you will find out what the most profitable side of electronics disposal is hiding. In many cities, there are stationary or mobile points where people can bring old devices. They are often organized by municipalities, environmental organizations, or the recycling companies themselves. These points can be located in shopping centers, near supermarkets, or on separate sites. Campaigns and promotions are regularly held, during which large retail chains or electronics manufacturers organize temporary collection points. This encourages people not to throw away e-waste, but to turn it in for recycling. Some companies offer services for picking up old electronics directly from homes, especially when it comes to large devices like refrigerators or televisions. Large volumes of electronic waste come from companies, offices, educational, and government institutions. When companies update their computer fleets, servers, telecommunications equipment, they enter into contracts with specialized disposal companies. This allows them to comply with environmental standards and ensure the secure destruction of data. For a business, the destruction of confidential information from hard drives and other media is extremely important. Recycling companies often offer services for certified data destruction before recycling. In many countries, there are laws that require electronics manufacturers to be responsible for the life cycle of their products, including their disposal. Write now in the comments from which country you are watching us. Manufacturers can pay contributions to special funds or organize their own collection and recycling systems. This encourages them to develop products that are easier to recycle. They cooperate with recycling enterprises that are part of their network, ensuring a flow of used electronics. Scrap metal collection points. Although not specializing exclusively in electronics, some scrap metal collection points also accept electronic devices, considering them as a source of metals, including precious ones. However, this path often does not ensure optimal recycling and can be less environmentally friendly. Unfortunately, there is also a shadow market. Significant volumes of electronic waste are illegally exported to developing countries, where they are disassembled in artisanal conditions, causing harm to the environment and human health. However, the legal recycling enterprises we are talking about operate within the legal framework. When the electronics are collected, they are transported to the centralized warehouses of recycling plants. There, they undergo initial sorting. Large batches of a single type of electronics, for example, only old computer boards or only mobile phones, can be separated to optimize the further processes of disassembly and extraction of valuable materials. Thus, a whole stream of electronic devices enters the warehouse of a recycling enterprise, ready for their valuable components, including gold, to get a second life. After the trucks deliver mountains of electronic waste to the recycling warehouse, the first and very important stage begins: manual disassembly. At this stage, teams of qualified technicians and operators work. This is not just breaking old devices. It is a systematic process aimed at maximizing the extraction of valuable components and separating hazardous materials. Each workplace is equipped with the necessary tools: screwdrivers of various types, pliers, wire cutters, as well as specialized devices for safely opening cases. Proper lighting and ventilation are also important, as some components may contain harmful substances. Workers must wear protective equipment, gloves, goggles, and sometimes respirators. The process begins with relatively light devices, such as laptops, desktop computers, and televisions. Specialists sequentially disconnect the main units. Lithium-ion batteries, found in laptops and mobile phones, are removed first. They are potentially flammable and contain valuable metals that require separate recycling. Printed circuit boards are one of the richest sources of gold, as well as silver, palladium, and copper. The boards are carefully removed from the cases. Central processors and RAM modules are especially valuable, as they contain significantly more gold than other parts of the board, so they are often separated for separate, more intensive processing. Each removed component is placed in a special container. For example, one container for printed circuit boards, another for processors, a third for batteries, a fourth for aluminum parts, and so on. This sorting is critically important, as it optimizes the subsequent stages of recycling. Components with a high gold content will be sent to more targeted and intensive extraction processes. After the initial manual disassembly and sorting, when components with a high gold content, such as processors, memory, and gold-plated connectors, have been separated, much more targeted and intensive processes for their recycling begin. These methods are aimed at the most efficient and economically viable extraction of the precious metal. They combine mechanical, chemical, and sometimes even electrochemical approaches. The first step is often further mechanical processing to further concentrate the gold-bearing material. Processors, for example, consist of a ceramic or organic case, metal contacts, and sometimes metal covers. These parts need to be separated. This is usually done with the help of special shredders or milling machines that allow for the separation of the metal legs or contacts from the main part. Some processors may be subjected to thermal shock to crack the ceramic case and release the gold-bearing parts. The separated gold-bearing metal parts are crushed into small granules or powder. This process increases the surface area of the material, which is critically important for further chemical processing. Usually, crushers are used, and then granulators, which grind the material to a fraction size in the range of 0.04 to 0.4 of an inch, and sometimes even smaller. After crushing, gravity separation may be applied, for example, vibrating tables, centrifugal separators, or hydrocyclones. Since gold is significantly heavier than most other metals and non-metallic impurities, these methods effectively separate fine gold particles from lighter materials, creating a more concentrated, heavy metal slurry. For large volumes of gold-bearing concentrates, especially if they contain a significant amount of copper or other base metals, high-temperature smelting is used. The concentrated powder or fine granules may first be sintered or briquetted for more convenient feeding into the furnace and to reduce dust losses. The material is loaded into special electric or induction furnaces. Temperatures can reach 2,500 degrees Fahrenheit. During smelting, lime or silica is added, which reacts with oxides and other non-metallic impurities, forming a low melting slag. Gold, like other precious metals, has a high affinity for molten copper or lead. Therefore, during smelting, gold dissolves in larger volumes of molten copper or lead, forming a so-called black copper or lead alloy. This alloy is then separated from the lighter slag. The alloy can then be further purified in converters, where air or oxygen is blown through the melt to oxidize the remaining base metals, which then pass into the slag. The output is an enriched alloy containing copper and all the precious metals. After removing the main part of the base metals, the material is treated with reagents that dissolve gold. After dissolving the gold, the solution is filtered to remove undissolved solid residues. Then the gold ions are separated from other metals using various methods. Gold is precipitated from the purified solution by adding reducing agents. These compounds reduce the gold ions to a metallic state, forming a pure gold powder. The gold powder is thoroughly filtered, washed with distilled water to remove residual chemicals, and dried. The resulting gold powder is melted in high-temperature induction furnaces and cast into ingots or granules. At this stage, high-purity gold is already obtained, often 99.9%. Every year, over 500,000 bridges are built worldwide, but only a few of them challenge nature and time. To create a giant capable of withstanding thousands of tons of steel, windstorms, and earthquakes, engineers first dive into the very heart of the Earth, drilling the ground to a depth of over 100 meters, studying every layer of rock. Here, under water and mud, the foundation is born, on which the fate of the entire structure depends. How do machines weighing as much as houses place piles with millimeter precision? And what will happen if even one of them shifts? Watch until the end, and you will learn what the engineering elite keeps silent about. The construction of long bridges begins long before the first steel beams or concrete supports appear. It all starts with a site investigation. Engineers analyze the soil, the strength of the current, the level of seismic activity, and the depth of the bottom, if it's a river or a bay. Often, special drilling rigs are used to take rock samples at depths of over 300 feet. These data determine the type of the future bridge: suspension, cable-stayed, or beam. After this, a three-dimensional model is created. It takes everything into account: the load from transport, the force of the wind, temperature fluctuations, and even the possible impact of waves during storms. For bridges longer than half a mile, the permissible error in calculations can be no more than a few millimeters. Otherwise, the structure may lose stability. When the construction of a bridge moves from drawings to the actual ground, one of the most responsible and complex stages begins: the construction of the foundation, or the pile foundation. It is these structures, hidden under water or earth, that support the weight of the entire bridge. Thousands of tons of steel, concrete, transport, and even wind load. Drilling cranes arrive at the site, giant machines with a long mast, a hydraulic drive, and interchangeable drills. They can reach the height of a 3-story building. Steel piles are brought to the worksite. Usually these are pipes with a diameter from 3 to 6 feet and a length of up to 100 feet. In marshy or marine areas, The piles are even larger, sometimes up to 150 feet. The drilling process takes place in stages. The machine is positioned with an accuracy of a few inches. For this, laser and GPS systems are used. Then the operator lowers the drill into the ground. The powerful rotation of the bit crushes the rock, and a hydraulic system pumps out the resulting pulp. In some areas where the soil is unstable, drilling is carried out with the immersion of casing pipes, metal casings that prevent the walls of the well from collapsing. When the hole reaches the specified depth, a steel pipe, the pile casing, is installed in it. A reinforcing cage is lowered inside, which strengthens the structure, after which concreting under pressure begins. Through a special hose, a concrete mixture is supplied from the bottom up, displacing water or mud. Thus, a dense, air-free mass is formed, which over time hardens into a monolith. In marine areas, floating barges with drilling rigs are used. Divers control the position of the pile underwater, and engineers monitor the process with ultrasonic sensors. In a strong current, drilling is carried out only during periods of calm, when the wave level is minimal. When the piles are installed, their tops are cut to the required height, and capitals are mounted on them. Large concrete blocks that unite several piles into one support. After this, pylons or columns are erected on these foundations, which are already visible above the surface. On land, temporary sites are simultaneously set up. These are logistics centers where beams, cables, reinforcement, and concrete sections are stored. Often, huge cranes 300 feet high are used here, which can lift blocks weighing over 200 tons. When the supports are ready, the turn of the superstructure comes. For bridges of great length, two main technologies are used: suspension and cable stayed. In a suspension bridge, the main load is carried by steel cables. To secure them, two massive towers, pylons, are first erected. Their height can reach 700 feet, as in the Golden Gate Bridge in San Francisco. The towers are assembled in sections, lifting each one with a crane and connecting them with bolts and welding. After the installation of the pylons, the main cables are stretched between them. This is a complex process that is carried out in stages. Thin steel wires, the thickness of a finger, are stretched one by the hundreds, until a main cable several feet thick is formed. Then vertical hangers are attached to these cables. They will hold the roadbed. In cable-stayed bridges, the main load is transmitted through inclined cables that go directly from the towers to the sections of the roadway. Such cables are made of steel strands with a polymer coating, capable of withstanding a load of over 500 tons. They are installed with the help of hydraulic winches, which precisely regulate the tension. The installation of the span sections is one of the most impressive stages in the construction of a bridge, when the giant engineering structure literally begins to connect the shores. Each section is a finished fragment of the road, made of high-strength concrete or steel at a specialized plant. There they are formed in giant molds, reinforced with steel bars, treated in thermal chambers for rapid strength gain, and then marked and checked for accuracy with a laser system. After this, these blocks are transported to the construction site. If the bridge is laid across a body of water, the sections are delivered by barges, floating platforms capable of withstanding hundreds of tons. On land, they are transported by multi-axle trailers with dozens of wheels, which evenly distribute the weight. The movement of such columns is usually accompanied by police, as each block can be from 100 to 400 tons and over 100 feet long. At the construction site, floating cranes or lifters are already waiting. These are powerful lifting systems capable of lifting a load of over 500 tons. Most often, such cranes are mounted on pontoons or mobile platforms that can accurately maneuver over the water. During the lift, the crane operator coordinates his actions with the engineers who are on the bridge supports. Every movement is a matter of inch precision, as the section needs not just to be lifted, but placed perfectly in the design position. When the block is suspended above the supports, it is slowly lowered. Workers fix the position with the help of special guide pins and laser marks. Then dampers and high-strength connecting bolts are installed in the joints of the sections. It is important that the sections fit together without the slightest misalignment. Even an error of half an inch can cause uneven load. Next, the joints are filled with cement mortar under pressure, which fills all the voids and forms a monolithic connection. In some types of bridges, post-tensioning cables are used, steel strands that are threaded through the internal channels of the sections and tensioned with hydraulic jacks, providing additional strength. If the bridge is being built over the sea, the installation is even more complicated. Barges with sections are tied to positions with an accuracy of a few feet using GPS, and the lifting takes place only in calm seas. Often at night, when the wind is weaker and the waves are minimal, the crane slowly lifts a section. The process can take several hours. From the side, it looks like a giant aerial operation. A steel or concrete slab, as huge as a 2-story building, smoothly rises above the water or a gorge, moving with an accuracy of a few centimeters. When it is fixed between the supports, the bridge literally grows. Another span, another few tens of feet of road, which bring it closer to completion. In parallel with the installation of the roadbed, communications are laid, lighting systems, communication wires, pipes for rainwater drainage. Most bridges have sensors that measure vibrations, temperature, the tension of the cables, and even the concentration of salts in the air. These data are constantly transmitted to a control center. When the main structure is completed, the road surface work begins. The surface consists of several layers. The first layer is a special anti-corrosion compound that protects the concrete and metal. Next, waterproofing is applied, then several layers of asphalt or polymer concrete, about 4 inches thick. For suspension bridges, lighter materials are used to reduce the load. The final stage is the installation of railings, noise barriers, and the painting of steel elements. The painting has not only an aesthetic function, it also protects the metal from corrosion. For bridges over the sea, paints with the addition of zinc are used, which create a stable protective layer. After the completion of all work, the bridge undergoes a series of tests. Special trucks are loaded onto it to check how the structure reacts to weight. Vibration tests are also conducted. Engineers check how the bridge behaves during wind or the movement of trains and cars. If the indicators meet the standards, the object is put into operation. Imagine, you throw away an old washing machine, not even suspecting that it could live another life. But where does your appliance actually end up after it's been taken away at a discount or for free? Is it really recycled or just buried under a layer of earth? Behind every seemingly dead machine stands a whole industry of destruction, separation, and material revival. Giant shredders, magnetic separators, eddy current fields that separate aluminum from steel with centimeter precision. And at the end of the video, you'll learn something that's not mentioned in any trade-in advertisement. What really happens to your old appliance after it disappears from your home? Many major brands and electronic stores offer a trade-in program or free removal of old appliances when you buy a new one. For example, in the United States, companies like Whirlpool, LG, and Samsung have such programs, and in Europe, initiatives like the Waste Electrical and Electronic Equipment Directive are in place. The terms can vary. Some companies simply take the appliance, while others offer a discount on a new purchase. Whirlpool in the United States might offer a $50 to $100 discount on a new appliance for an old washing machine. LG and Samsung sometimes offer $100 or $200 as part of promotional programs. In Europe, some programs allow you to get up to 10% off a new appliance. But more often than not, the discounts aren't very large. Most companies view this as an environmental initiative rather than a way to attract customers. In many cities, there are electronic waste collection centers where citizens can bring old washing machines themselves. Often these centers work in cooperation with municipalities or private companies. In some countries, including Germany, the United Kingdom, and the United States, there are municipal services that provide collection services for large electrical appliances. For example, in New York City, you can order a free pickup through the NYC Safe Disposal program. Some companies are involved in secondary metal recycling, so they may buy the washing machine or take it for free. They send the appliance for dismantling, where they extract metal, electronics, and plastic. First, the machines are sorted into categories: working, partially working, and non-working. Working ones can be repaired and resold, while those beyond repair go to dismantling. Dismantling begins with removing the outer panels, doors, and drum. The motors, electronics, wires, and pumps are separated, as they can be reused or melted down. Metals are sorted separately: stainless steel, aluminum, and copper. Plastic parts are also sent for secondary recycling. This process can be done both manually and with the help of special automated lines that shred the casing and separate the materials using magnets and air separators. Automated lines for recycling washing machines consist of several stages, each responsible for separating different materials. First, the machines are fed onto a conveyor belt, where they are shredded by powerful rotary shredders. The blades of these shredders are capable of tearing metal and plastic casings into fragments ranging from 3 to 10 centimeters in size. After shredding, the materials pass through magnetic separators. They attract ferromagnetic metals, such as steel and cast iron, separating them from the rest of the components. Next, an eddy current separator comes into play, which uses a magnetic field to push out non-ferrous metals, including aluminum and copper. Plastic and light materials are separated using air separators. Powerful streams of air lift the light particles up, sending them into special containers, while the heavier ones remain on the conveyor. At the end of the sorting line, the remaining materials are additionally checked with optical scanners that analyze their composition and direct them to the appropriate sections for further processing or disposal. After the materials have been sorted using air separators and optical scanners, they go to separate processing lines. Plastic, metal, glass, and other materials are processed for further use or recycling. The remaining metals, such as steel parts, are sent to metallurgical enterprises for remelting and further use in the production of new goods. Magnetic separators effectively extract iron and steel, which are sent for remelting. Plastic parts are shredded and pressed into briquettes. These briquettes can be sent to specialized enterprises for the production of new plastic products, or for use as secondary raw materials for new technical devices. If the washing machine has glass elements, for example, doors or windows, they are thoroughly cleaned of any contaminants and can be melted down to produce new glass. The remaining materials that are not recyclable, for example, certain types of rubber or mixtures of materials, are sent for disposal or burial at specialized landfills. Such sorting and recycling lines significantly reduce the amount of waste that ends up in landfills and help return raw materials to the economic cycle. In some cases, for particularly complex materials, additional technologies are used, such as thermal decomposition or chemical treatment. They are used for materials that cannot be simply separated by mechanical methods, or that require additional processing to prevent contamination or harmful emissions. For example, some plastic components that contain a combination of materials such as plastic with metal inserts or rubber parts. Such materials may not be subject to simple sorting and require special processing to separate the components. Often, rubber elements, especially with the addition of chemical compounds, are not effectively recyclable due to their complex structure. For such materials, thermal decomposition or other chemical processes may be used to break them down into simpler components that can be reused or disposed of. In some cases, when an appliance contains toxic substances, for example, mercury in old relays, batteries, or lighting devices, such materials must be processed by special methods. This can be a chemical process that neutralizes harmful components or isolates them for further safe disposal. Polyurethane or polyester materials, which are often found in wire insulation, or in various components of household appliances, can be subjected to thermal decomposition to separate them into simpler components that can be recycled. In cases where washing machines or other appliances contain complex composite materials that have several layers of different substances, for example, plastic with metal or fibrous components, special processing may be required to separate these layers and for the subsequent recycling of each of them. In general, such technologies are used to ensure maximum efficiency of disposal and to reduce the negative impact on the environment, as improperly processed materials can lead to pollution or the leakage of dangerous substances. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which with filigree precision extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify, like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials.